Hi, everybody. Thanks for tuning into this session today. My name is Andrew Lee. I'm an assistant professor at Carnegie Mellon, and I'm going to be talking about sublinear time algorithms for offer set optimization. My co-authors are Vivek Farias and Deeksha Sinha, both from MIT. So what do I mean by offer set optimization? Well, I want you to think back to the last time that some firm or platform recommended a set of items to you. This is almost certainly in the last 24 hours, if not in the last hour. Maybe you were reading a news article or a sequence of news articles, and right below your current article was a set of recommended links that you could follow. Or something that many of us have done very recently is you were grocery shopping online, you had added some items to your shopping cart, and then something like this came up. In all of these cases, the firm here was choosing among some massive set of items, a much smaller subset to recommend to you, personalized to your very recent behavior with some objective in mind. Now this problem, as I've just vaguely described, is very well studied. Here's kind of a representative mathematical formalization for it, and a quote-unquote ideal way to solve it, right? So imagine we have we now being the firm or the platform, we have a set of items, script v. It has n individual items, little v1 to little vn. There's a set of user types, script u, and we'll talk a lot later on about what exactly these types represent, but suffice to say a single type represents a certain behavior of a user. Kind of most important is we have a reward function which maps any subset of the items and a single user type to some non-negative reward. Then kind of our main problem that we're trying to solve here is that given a random user, capital U, and some upper limit on the size of the set that we can recommend, the goal is to maximize our expected reward, the expectation being over the randomness of the user. And again, we're choosing capital S, a subset of items subject to cardinality constraint. Now I want to pause here for a moment and emphasize again this fact that we are modeling the user as being random over the types. That's very important here. The purpose of this is not to model a population of users that individually take on different types, but rather to model the uncertainty in our estimate of the type of a single user. So for example, going back to the grocery shopping, if we've observed that a customer has added a few items to the shopping cart, that does not mean that we've pinned down their type exactly. Okay, and the randomness here is meant to model that uncertainty, the uncertainty in our estimation. And we'll see in the next slide that ignoring this uncertainty is kind of the status quo that we're trying to beat here. But back to the modeling here. So this quantity, we're going to call this opt. And for the rest of the talk, when I refer to opt, I mean precisely the maximum value here. I'm going to make two assumptions right off the bat, even within this idealized framework. The first is that, just to make things easier, rather than letting our random user u be kind of an arbitrary random variable, we're going to say that it's in fact uniformly distributed over m different types, little u1 through little um. Just as a sanity check, that means the expectation here in our opt, we can replace that with this summation. Now this is not really a necessary assumption, this is really just made for the sake of this talk. In reality, we show that if u is an arbitrary random variable, you can just sample a finite set of points from u and treat it as uniformly distributed over those points. and that the number of points you need to sample is small. Our second assumption, though, is very much important. We're going to assume that our reward function f for any fixed user type as a set function over the set of items is monotone submodular. Now, in the context of recommender systems, this assumption is fairly innocuous, right? We can think of the reward function there as being a conversion probability, right? So in the case of recommending web links, f is just measuring the probability, that you click on one of the recommended links. On the other hand, in the area of assortment optimization, where the goal is to recommend an assortment of products to maximize the total profit in the end, it's no way guaranteed that f is submodular. Still, there's recent work showing that assortment optimization under certain choice models, a subset of mixed multinomial logit models, for example, does in fact preserve submodularity. But I don't want to dive too deep here. The point is, the model as we've set it out here is fairly generic, fairly representative, and the great thing is the fact that submodularity buys us a constant factor of opt using our favorite greedy algorithm. And moreover, this runs in linear time. In time kmn, where k is the size of the set we're recommending, m is the number of user types, and most importantly, n is the size of our item set. So I'll tell you right now that during this talk, we will not do any better than a constant factor of opt. Right? And so you might say, well, if we've already achieved that with an algorithm whose runtime is already linear in the number of items, why don't we just pack up and go home? And the problem that we face in reality is that this algorithm is unfortunately only linear in the number of items. Right? And the reason this is a problem is that when we're trying to do offer set optimization in real time, say the time between the last web link viewed and the current web link, we really only have milliseconds to make this decision. And when n is on the order of millions, that actually rules out even linear time algorithms. So the purpose of this talk is to answer the following question. Can we approximate opt in sublinear time, that is time little o of n? Now, sublinear time means not even enough time to parse through the item set. So at first glance, this might seem impossible. But if we look at kind of the current practice right now, we'll see why there's actually hope to do this. So any modern recommender system works by kind of encoding preferences inside some metric space, which we'll denote with a script m and a metric d. And what I mean by encoding the preferences is that both the items and the user types get embedded into this space. So our items script v and our user type script u are represented as subsets of this metric space. Right? The preferences get encoded in the distances in the sense that the distance between v and u is inversely related to the affinity of user u for item v. Okay. And suffice to say right now that we're very good at estimating these metric embeddings from data. This is never the challenge. Now, the way real-time personalization is currently done is this embedding is estimated from past data, and this gives us a representation of every item inside some metric space. Then when a user arrives and say checks out a few websites, a single point in that metric space is chosen to represent the user, and then the nearest neighbors to that user are returned as the offer set. Now this quote-unquote works because many metric spaces actually allow for nearest neighbor queries to be done or approximately done in sublinear time. So there we go. We've actually met the sublinear time requirement. On the other hand, the lack of sophistication here is kind of why real-time personalization often feels so low quality. So coming back to this image from grocery shopping, this is actually a real image I generated. The items I had added to my shopping cart are basically the full recipe for guacamole. And I think what's missing from this recommendation here is, for example, tortilla chips. So not great, but what we want to keep from what we just saw is this underlying metric structure. So going now to our kind of our final model, we want to keep the fact that preferences are encoded in this metric space. We'll stick with this notation of a script M and a metric D. We'll stick with the fact that our items and our user types are embedded in this space, and that somehow the distances kind of capture the inverse of affinity. To make that more precise, I want to tie that metric to our reward function. And what we'll say is that there's a function p which translates distances between items and user types inside the metric space to the reward obtained from offering that single item to that user type. And that inverse affinity is captured by the fact that this function p is non-increasing. And by the way, I've chosen the letter p here because p is actually going to represent a probability very soon. At this point, we've effectively stated the entire model, and this link we just established between the metric space and the reward allows us to state the main idea that we're going to try to leverage here, which is that if you can carefully sample a sublinear sized subset of the items, then in fact it suffices to just run greedy on that subset. And in particular, we actually show that the loss is quote-unquote small, in a way that I'll make precise soon. The loss is quote-unquote small if we're able to sample each item proportional to its individual reward, its reward if it was offered as a singleton. Tying back down to this function p that links back to the metric space, it'll actually suffice to sample each item with probability equal to p of the distance. Now I'm hiding a few non-interesting steps here, but suffice to say, the problem, our entire offer set optimization problem now can be reduced to the following problem, which I'll call sublinear time sampling, which is that we require some sort of randomized data structure that for any user type u has two properties. First, it returns a subset of the items such that the probability of any single item being included in that subset approximates our target probability, which is p of the distance from v to u. And by approximate, I mean within a multiplicative factor of 2. The fact that it's a 2 here doesn't really matter, by the way. The second attribute of this data structure is, of course, that it has to run in sublinear time. Now, the key fact, which is going to drive our entire approach and guarantee, is the fact that this data structure does exist basically whenever we can run approximate near neighbors in sublinear time. The field of approximate near neighbor algorithms, by the way, is developed enough that at this point any metric space we would use in practice falls into this category. Now I want to give kind of intuition behind the construction of this data structure and why it's even possible. And I'm going to try to do that just with pictures. So here goes. So imagine that this is the target function that we're trying to sample from. So we fixed some user type u. On the horizontal axis is the distance to u, and the vertical axis is the probability with which we're trying to return each item. To approximately sample from this distribution would mean actually sampling within this dotted range above and below. Now, what exactly is the link between this sampling and near neighbors? It's actually the following. So let's look at the exact near neighbors problem, right? Which is to return all items in script v within some distance gamma. The key observation is that that's actually I mean, it's weird to think of it this way, but that's a sampling problem. It's sampling according to the following curve, right? Which is 1 for any distance below gamma and 0 for any distance above. Exact near neighbors is never interpreted this way, but it is equivalent, right? Approximate near neighbors, and this is the first time I'll formally state what it means to solve approximate near neighbor, right? Is to achieve the following. It's to approximate this piecewise constant curve in the sense that for any distance less than gamma, the return probability is greater than some 1 minus epsilon. And then very quickly beyond gamma, the probability decays below 1 over n. This is accomplished, for example, by locality-sensitive hashing, which is kind of the state-of-the-art in approximate near neighbors, which samples according to a curve like this gray one here. Now, our approach, which we call locality-sensitive sampling, combines those approximate near neighbor structures in a way that is able to sample from any function with only a logarithmic increase in running time. The net of all of this is our final result. We're able to approximate opt in a runtime that is, you'll see, n to the alpha. And most importantly, that alpha is less than 1 whenever that metric space allows for a sublinear approximate near neighbors. So I'll conclude by describing an experiment that we ran with data from Outbrain. So before it was acquired, Outbrain was kind of one of the main players in web content delivery, right? The problem of recommending web links after you've read some articles, let's say. The data we had was this large set that came from 2 weeks kind of across the US. What we did was we estimated 100-dimensional embedding of the web pages. And then for any algorithm, we gave, for each user, the first 10 pages viewed and asked for an offer set and compared it to the pages that user had actually viewed as a proxy for choice here. We compare our algorithms to 2 benchmarks based on single near neighbor queries, one taking the nearest neighbor of the last viewed page, the other taking near neighbor of the average of the last few pages viewed. And comparing hit rates, we can see a pretty meaningful improvement using our own algorithm. So that concludes my talk. Thanks for tuning in. I'll be around afterwards for questions. Thanks a lot. Bye.